Good morning. Welcome to Krishna's classroom. Last time, towards the end of the lecture, we looked at the norm, the concept of norm on linear functions. Probably it needs a further detailed consideration because there are some nice structures around. So let us take it up in this talk. So let me set up the preliminaries. We call let X be a normally linear space. Normally linear space over K. K stands for R or C. And depending on if it is R, then you say X is a real normally linear space. If K is C, then we call it a complex normally linear space. Okay, so we have not set any norm. So this is just a linear space. Right. Maybe I think at this stage I can avoid this N and then write and norm space. Right. Now, that means on X what is a norm? A norm is a non-negative real valued function on X with the following properties. Greater than or equal to 0. So these are the properties that are required. So it's a non-negative real valued function. It's a non-negative function. That's enough. Say that. And norm of X equal to 0. Then X equal to 0. Then how it works on the product on the scalar, what is called scalar multiple of X. That is norm of alpha X is equal to mod norm of X. And on the sum, that is the addition, norm of X plus Y is less than norm of X plus norm. Now this is C leads to what is called the triangular. Now naturally the norm induces a metric the distance so it becomes a metric space. So X is naturally a metric space. This induced. So now we work on what are called. So what is a linear function? F is a linear function F is a map from X to K, which is now this means F of alpha x plus beta fy for every alpha beta belonging to K, xy belonging to so it's a linear map from X to K, and this is what is called a linear transformation. Okay, both are X is the given norm, the given normed linear space, and K is essentially another normed linear space. That is, it's either R or C, which is the usual normed linear space. So both are linear spaces, and therefore the F that you have is a linear transformation, in the sense that it is a linear map from a normed linear space into another norm. To be a linear transformation, it is not enough, not necessary to talk about the norm. Okay. Now, let us consider the case f equal to 0 is fx equal to 0. This is a trivial linear transformation. And that is not of much interest to us. We are not interested in all that. We are interested on non-trivial linear transformation. So this we shall just keep there. It's a trivial one, and whatever follows there is the corresponding things that. Okay. So let us write down. Consider now this linear transformation from x to k is called already linear. Now consider f not equal to 0. That means we are now looking at the case where the linear transformation is not equal to 0. What does this mean? This implies there exists so there exists a y in x which is a non-zero vector such that fy is not equal to 0. That's what we mean by saying that f is not equal to 0. Now consider the null space of now NF is a subspace of x and NF is a proper subspace which is the non-zero y for which fy is not equal to 0 is not in this class. Let M designate for convenience the null space of it. Now we consider quotient space by M defined by designate by x where and of course x plus m that's a definition of that. Now, there is something special about this. Now, note that equal to rather this is something. Yeah, let us work it out. So this is one of the properties. Now let us observe that if x1 minus x2 belongs to M, then x prime belongs to M. Okay. That's quite easy to see. Okay. So you can write the following. X1 minus therefore this implies what? X1 equal to x prime. Now M plus x1 plus M equal to x2 plus and this is equal to x prime plus M, and x prime plus M equal to M, because M is a subspace and x prime therefore you have x1 plus M equal to x2 plus M. You can easily work it out. So you can actually show that if you take an element of x1 plus M, that is in x2 plus M under these conditions. Conversely, x2, an element in x2 plus M is in x1 plus M. Or they are same. That will be the way in which actually this I have written a short and shown how it comes. Actually, you take any element of, so you consider take any y belonging to implies y equal to x prime, where x prime belongs to now hence y is equal to So x1 plus m, x2 plus m, a similar argument. Would imply therefore this implies conversely x1 plus m therefore x1 minus x2 and this belongs to m because m is a subspace. Okay, so this is what we wanted, right? So you see that x1 plus m if and only this is the result. The collection explicit. So if x belongs to m, this would be simply 0. Okay. X by m. Now x by m this is quite easy to and is quite easy to check that all these properties are satisfied. The identity element is zero, which is the same as no. So the inverse element is this minus of x is the inverse element, and then of course you have defined this, then you can verify a vector space x by m is a vector space over this one. Over k. Now the natural question that you ask is, what is going to be the dimension of this space? For that, here M is not any, all this analysis goes for any subspace M. Okay, but we are taking M as the null space of a linear function. Therefore, what more you can say about this space? Let us work it out. So we prove that is 1. Okay, right. Now, since f is not equal to 0, that implies y does not belong to Y does not belong to M, which is the null space of Now we observe the following. Suppose if X2 now that is something that we want to do. In fact, let us just have a look at the scenario in R2. In R2, we make the following observation. R2, before that, let me write the following. Is a maximal proper subspace of what do we mean by a maximal proper subspace? Now another terminology is hyperspace of hyperspace of okay. This is the case that it's a null space of a linear and the linear function is trivial, is non-trivial. Take x by m. Okay. X by m, suppose we first observe that, so we started with a y. Okay. So element of now you observe the following. So you take any x1. What is x1? Take x1 to write as x1 if possible. This is true for for this choice of for any case. Now choose k such that x minus ky belongs to is it possible? This is the question. So let us see. If it is so, then f of x1 minus ky equal to 0. That is f of x minus x being linear equal to 0. Now choose k is possible. Why? Fy is not equal to 0. Therefore, choose such that therefore this is well defined. Hence, x1 can be written as x1 minus x1 f of x1 y so this is in M and this is a scalar multiple of this scalar. Okay. Similarly, equal to a2y such that and k2 is a scalar, or k2 is equal to so each element is of this form. Okay. Therefore, this is for any arbitrary element. Now what you have x1 equal to, I'll write it this way, x1 prime k2y okay, equal to 0. K1, K2 are scalars. Therefore, x1 minus x2 equal to okay. So from this relation, it follows that x1 minus x2 belongs to M and y is not equal to 0. Therefore, y does not belong to M. And hence, the only possibility is that, so we observe the form. Equal to 0. That is of x1 equal to so in such case, x1 equal to 2. Okay. So let us look at this. So we have seen x by m is a vector space and x1 bracket x1 equal to bracket x2 if and only if x1 minus x2 belongs to. Okay. What is the implication of this? The implication of this is this. All right. Okay, we prove this. Y is such that f of y is not equal to 0, which we have fixed. So how do we prove this? Take any element in x by m, show that it is spanned by a scalar multiple of y plus x. Is a that is or in other words, x minus ky belongs to m. Some how do you prove this? We have to we have already chosen k. x1 and x2 are two elements, then x1 belongs to we have already proved this. Okay? Because we have shown that if you take x1 x minus ky, where belongs to m. So what do we want to prove this? That This is the structure of X. Now, take any X and Y belong to X. Sorry. Then you see that x1 equal to for x1 plus x2, y, okay, but this is equal to because of linearity, therefore x1 plus x2 now you see the components, whenever you pick an x belonging to then x is equal to y, where x prime and k uniquely determined. So there is a unique representation. How do you prove that? Suppose x is equal to x k1y, x is also equal to x2 prime plus k2 okay. Then we have 0 equal to k1 minus k2. Now this part, this is in M and this is does not belong to M, or what you call Okay. This does not belong to. So what is the implication? As such, when K1 is different from K2, therefore, you see that this implies equal to 0 equal to some x3 prime belongs to M, and okay, so this means so there is a unique representation. This is important. Okay, I mean that's a beauty, right? So let us now just look at an example. That example would give some insight. Now you take so M you take as a hyperspace in R. This is R. So a hyperspace is a line passing origin. Okay. Now you can see that you have a y not equal to 0. Y not in okay. Now let us see what is we just see what is x plus or what is this? So it consists of all x1 and x2 the property that and you see that so what does this mean? See, you look at M plus R2. See, M plus R2 in this case is a line parallel to M and passing through why it is so. So you take two x1 and two elements of this. Suppose this is your so what is x1? See, you want to get x1 by adding something to y. What is that? You apply parallelogram. Therefore, this is y x1 minus. So you want x1 minus y belongs to M. Okay. So you see that x1, x2 if and only. So you see that you take any x2 here, you take on the line parallel to this, to see that this is equal to x2 minus y, and x2 minus y belongs to. So x1 minus y belongs to M and x2 minus y belongs to M. So you see that x1 equal to x1 minus x2 belongs to M. What is x1 minus x2? x1 minus x2 in this case is going to be y. Okay. So you see that means both I will put it this way, on the same line parallel to, that is the point. You see you have that. So now you see that any, suppose you take x3 here. So all x's is related the relation So this is the scenario that you, okay. So this is x plus Okay, this is y. Sorry. Or which is equal to now what you do is you take the line spanned by okay, right? So let me designate that by L. Designate, right? Okay. So any x such that x belongs to ky. So because comes from the fact that x is equal to so this is the reason why you okay. Hence x is equal to union of all k belongs to k. That is one thing. Further, k. This is k1 equal to k2, right? Otherwise, they are different. That is ky plus m intersection So what do we have? The space is now divided into several lines parallel to the given line. So R2 is the disjoint union of lines parallel to subspace F. In R3, now we take up the case in R3. A hyperspace is a plane through the origin. So this is a plane passing through the. Now what are the, suppose this is y. Suppose y then so you have a parallel plane. In fact, what you get is this, analogous to this one. You have R3 is disjoint union of yeah, that is And where so you take the line spanned by y. Since y does not belong to M, implies the line say L. The vector y does not lie or ky plus M parallel to M and ky So this is the geometry of the the these plates, the stratification of R3. Okay. So in every vector space, see, to take a non-zero linear functional, then the null space of the linear functional is a hyperspace, and the translates of hyperspace are the elements of the space x by m, and x by m is therefore spanned by the vector, the element y plus m, right. which is not equal to 0. Okay, right? So this is the basis. So one-dimensional vector space. So in all situations, x by m is a one-dimensional vector space which is spanned by the element bracket y, where y is not equal to 0. Y does not belong. This is the scenario. Now let us work out what this is. Now for any x belonging to now what about fx? So fx is going to be equal to f of, which is equal to f of x prime plus k times f prime. F is linear, but that is equal to 0 plus therefore once we have y fixed, fx is equal to so this is the, or we can even write this now f of, now define on the one dimension space. Okay, define this to be equal to k times e. So alpha, k alpha. Now let us compute the norm of y. Sorry. You see that if mod fx, this is equal to modulus of k into alpha. Fy So we have this is equal to suppose we have chosen y such that equal to 1. That you can choose, okay, because we are only considering the whole space now. Okay. Oh, did I not say what is norm x? See. Now, norm of k, we define it as follows. This is the unique representation. Okay. Then this is equal to, and what is that? This is equal to, therefore norm x is equal to, see, we take norm of x prime equal to 0 and this one. So we started with the normal system. Now we have chosen, since norm y is set equal to 1 by choice, we have this is equal to mod. Now let us write down this. So what is it? Norm of f is equal to supremum of which is equal to okay, what is that? Fy is equal to alpha. Okay, sorry, Fy is equal to alpha from this consideration. Fy is equal to norm of f equal to, this is Fy, this is alpha divided by 1, and this is the, so this defines the norm of if y is not taken as 1, then it will be mod alpha into mod q. So this defines the norm. Okay. So that's about the norm of the linear. So what you have is a one-dimensional vector space is there, and then you see that f is a linear functional, f defines a linear functional on that one-dimensional space. Therefore, whatever f you set, see, yeah, whatever you set for y, then suppose the norm of y is equal to 1, then you see that the norm of ky is going to be mod k into norm of, this is the norm value. Okay. So x by m is a normed F space. Now that is the model. Now we are in a position to introduce what is called the so-called Banach theorem next time. Thank you very much. So one thing that you should understand is this, that this x by m is a translate of the subspace M, where the subspace M is the null space of F. You take the null space of F, translate it through a vector, and then you get parallel planes and or parallel spaces, and these parallel planes or hyperplanes are the so-called elements of the bracket or x by m, elements of the space x by. Now you can define the norm of that, or there is a norm that is naturally induced from the norm that you have on the vector space, and taking, of course, naturally that will involve the definition of f. You see that it actually depends on what value you assume at y for f. What value f takes at y once you fix y. If it is alpha, then this is going to be norm of f. Thank you very much.